Okay, so we see in the solution, the first one, part A, is very simple. You just use straight out momentum. All we're looking for is the momentum of that one object. This is really not a conservation of momentum because there's not two objects colliding. It's just momentum. Okay. And notice we come to 1.2 to the fifth kilograms meters per second. Part 2, we were comparing what? The momentum of, we're comparing what is the speed of a 2,000 to have the same momentum. All right, so we are comparing the momentum of 2 to the momentum of 1. And so basically we just set them equal to each other because their momentums are equal. Okay. All right, because it tells us that. Then we want to find what the speed is. Well, notice that the speed is pretty high. It's a lot higher than it was. It went from 12 to 60. Okay. 5 times greater, in other words. Okay. And then part C, the kinetic energies were the same, and so he just sets one equal to the other and solves for it. And there you go. All right, that's 144 multiplied times 5,000, right? All right. Oh, good Lord. No, times 5. Sorry. Okay, good. Good. Yeah, close enough. Close enough. All right, good job. All right, so hopefully you've got that one. That one's copied down. Now let's look at another one, and let me pause for a minute. Okay, so we see with this problem, this is number 2. Number 2, okay. Where? Right here? There we go. Very good. Yeah, you've been watching me write too much. You're starting to adopt my handwriting. I hope not. All right. All right, so all we had to do, y'all, is take our momentum equation and throw the trig in for the x and for the y. That's all you had to do. Now, if we wanted to find the magnitude, what would that be? How would we do that? Yeah. Square the squares. And then do the angle, do arctan. Okay. All right. So we want to find the momentum's magnitude. Square the squares of those two figures right there, numbers. All right. All right. Very good. Very good. All right. I want to stop for a second because I wanted to do this the other day and I forgot to do it. All right. Kind of regress. Okay, so let's look at number 11. All right, let me write down what we've worked. We've done what? Number 1, number 2, we're fixing to do number 11. All right, good. Okay. All right, so number 11. And I'll write them on there. All right, says, all right, at time t is equal, at time 0, so at time 0 seconds, a 2,150 kilogram rocket, a 2,100 mass is equal to 2,150 kilograms. In outer space, fires an engine that exerts an increasing force on it in the x direction. Okay, so the rocket's going this way. There's one of its fins, and there's another one. Okay. And it's in the x direction. That's the x. That's the y. Where Fx, force in the x direction, is equal to a t squared. Where t is time and has a magnitude of 781.25 newtons. Okay. So the force has a magnitude of what? 781.25 newtons. Okay. All right. Find the when t is 1.25 seconds. So then at t is equal to 1.25 seconds. Find the SI value of the constant A, including its units. Okay, so we've got to find the constant A, right? We've got to find that. Okay? Okay? All right. Now notice it gave you F. It gave you that right there. So let me pause a minute. All right, so we just solved for A. It's just algebra. Now let's look at part B. Part B. What impulse does the engine exert on the rocket during the first 1.5 second interval, starting at 2 seconds after the engine is fired? All right, so do we understand what it's saying? All right, let's write it and then I'm going to pause. All right, so 11B. All right, so the rocket fires its engine. Okay. Oh, whoa. There we go. Ignore that. All right, so it fires its engine. We know that A is what? 500 newtons per second squared. So it starts at 2 seconds. It fires engine for 1.5 seconds. So T initial is what? 2 seconds. T final is what? 3.5 seconds. So we want to find the impulse. Now remember that the force is a function of AT squared. F of x AT squared. All right. Don't forget that impulse is equal to what? Well, we got a function, y'all. So guess what we're going to get to do? We're going to get to integrate it, right? dt, right? Okay? So let's integrate it. So it becomes what? 3.5 to 2 seconds, and it becomes AT cubed over 3, right? Am I doing my integration right? Okay. So finish it. So J impulse, we know it's 3.5 and 2. So we got what? That is 500 newtons second squared times 3.5, yeah, over 3 minus, now look, I'm going to do this right here, minus, I'm going to drop over here, 500 newtons second squared times what? 2 seconds, and that's cubed, right? Over 3. And what do we get? 5812.5. Is that right? And what are my units? All right, there's a couple of different ways I can write this. All right, this becomes what? All right, we got seconds squared, so that's gone. This leaves me with what? Seconds, doesn't it? Newton seconds, right? Is that my unit? Huh? Yes. You integrate. It was AT squared, you got to integrate it. So that's a Newton second. All right, what is a Newton second in actuality? All right, y'all, we just talked about it. All right, a Newton second is what? Well, look, y'all. Now I'm telling you, you can't forget this. All right. Newton second, yeah. All right. So we do what? Hey, what is that? Momentum. But now remember, it is what kind of momentum? Impulsive momentum or changing momentum? Always remember, y'all, J is equal to delta P. Okay? Okay? J is equal to delta P. And in the lab, if you did the integration of that curve, you got a whole lot closer comparison. Well, I won't say, if you'd done the other part, I think most of you left a step out. If you'd just done the integration, you'd noticed it'd been real close. Somebody went back and fixed that, and you did get real close answers. Okay. All right. All right. Okay. 5812.5 Newton seconds, and that's typically when we're talking about impulse, that's the units we'll use. Even though it is a kilogram meter per second, we'll still just say Newton seconds, referencing that it's an impulse situation here. All right. All right. All right, and then part C. What was part C? By how much does a rocket's velocity change during the interval? Assume constant mass. Now that's always nice, but you know good and stinking well that a rocket going up is losing mass. So then it becomes a what? What would if we were to graph that relationship, what would it look like? The mass relationship versus velocity. All right, mass is decreasing, velocity is increasing, right? So it would be a what? Be what kind of mathematical curve? Yeah, well, if you put mass on the vertical and velocity on the horizontal, then it would be what? Okay, as the rocket's going up, is it going to lose or gain velocity as it's losing mass? Gain velocity. Okay, so if velocity is on the x and mass is on the y, then mass is doing what? Decreasing as you go up. Velocity is increasing like crazy, isn't it? Right? All right. No, wait a minute. I got it back. You're right. I got it backwards. I'm sorry. I got it backwards. You were right. I'm sorry. It's that way. I'm getting it backwards. Yeah. I'm sorry. So it'd be a parabola. Well, I had my axis turned around. I should have put velocity on the y, and there we go, and mass on the x. I had my axis backwards. Yeah. Well, got to be careful saying that. All right. Okay. So if you did it that way, then it would be what I'm trying to get you to see. It'd be an inverted parabola or hyperbola. Be hyperbolic, right? Well, with what you're talking about. What I was saying, mass and velocity. But if you put velocity on the y and mass on the x, then it would be parabolic. Which is basically what? An exponential relationship? Would it be like a quadratic? Yeah. So you can see how when those rockets take off, after what? 2 minutes, 3 minutes, they're moving at 15,000 miles an hour? Maybe not that long, because you have to consider losing mass as you continue to gain elevation. So, boy, you really start to accelerate. It's a curve. It's not a linear relationship. Okay, it's not linear. All right. All right. It's parabolic. Wow. What was that movie that came out here a while back about the ladies that worked out all the math for the... Yeah, at NASA. Yeah, I never did see that movie, but it's a true story. I want to go see it. Yeah, I need to see it, yeah. Pretty boring. What? Yeah. All right. Okay, so let's look now at the second part, the third part. Okay. So how much does it change during this interval, assuming we got constant mass? So this is what, 11c? So we got J is equal to what? Change in momentum, isn't it? All right. All right. Now, I want us to think here a little bit about. Notice we're talking about changing velocity. All right. So really we could say this, couldn't we? We could write it this way. All right. Because that's all it's asking. It's just asking how much would the change in velocity be. Correct? Because see, it didn't give us an initial velocity. All right. So delta V is equal to what? J over M. And our impulse was what? 5812.5. And that's Newton's seconds over what was the mass? 2150 kilograms. And yeah, and the change in velocity is what? 2.7 meters per second. Now again, assuming constant mass. Now how do you get that from Newton seconds? Come on now, we can't forget this right here. Meters per second squared. All right. Kilograms cancel out. That cancels, and you're left with meters per second. Okay?